Hello. So today I'm delivering a lecture on CNN, that is Convolutional Neural Network. Little thing about me, I am Aryan Mangla. I am an ex-intern at Intel and NVIDIA. So let's dive right into it. So we will explore computer vision here. So computer vision is nothing but basically how a computer see or how a computer vision anything. So what are the major categories or the broad categories which we can say that computer vision problems are in? So one of them is image classification, like you can see in this example, like cat and is this image and cat or not? So it will give the response based on it, like right, or yes or no. Then there is a problem of object detection, so that whenever you have seen in some of the videos or somewhere else that there are bounding boxes around the cars or different sources, so that's exactly it. So these are here. Then there is a style transfer, like which you see in your Snapchat filters or Instagram filters. So how we record ourselves, and that will be transferred into different style, like a Disney Pixar style or anything in that respect. So these are the broad categories in which we will be covering in our whole series. So first of all, I want to talk about edge detection. So what is edge detection? That let's take it with a very simple example. So suppose these are different edges, or these are different parts of the faces or anything else. So a combination, you can imagine that in a neural network, so in all of those different hidden layers, you can imagine that this is how each hidden layer imagines thing to make it. So the initial hidden layers will be seeing something like this, something like edges in this, and then it will be the later edges will do a more complex computation, and they will be able to see part of the faces, like they can see eyes, nose, and subsequently they can visualize the whole faces. That will lend us to all of the technology which we uses related to face recognition and everything. So this is a whole the computer vision problem really took off. So the basis of all them is how firstly a neural network, how firstly a single neuron detect what is an edge. So this is that. So like these can be divided into two segments, like vertical edges and horizontal edges. Here you can see, like, this is the initial base image. So you can see here are people standing in front of crib. So now these are divided into vertical edges, as you can see all these. So these are divided into vertical edges and horizontal edges. And now we will see next how we can actually write a function or a map that can help us identify these vertical and horizontal edges, among many other edges also. So yeah, firstly move into the vertical edge detection. So you can see this is a normal matrix. So imagine this is a kind of a compressed image. So each image can be shown into can be transformed into a matrix that is with a different vector, and it can be generally done into like height, width, and their number of channels. So let's say 64 into 64 into 3. So that's a 64 by 64 pixel image that is into 3 channels, that is RGB. So let's say for simplification we have now taken image part that is of 6 into 6 matrix, and it is being combined with the 3 into 3 filter. So what is a filter? Filter is a thing in a CNN that help us identify how each of that help us to compress the large parts into a smaller part, and it basically help us to preserve dimensions. Why it is important? Because in deep learning there are in generally in real scenarios there are a lot of images. So the dimension of real images is a lot. So let's say any normal pixel you've taken from your phone is roughly around 1000 pixels. So you can imagine 1000 into 3. That is a normal standard picture, which is not a very high resolution picture also with the modern standards. So that picture itself is equivalent to about 3 million pixels. So that is the amount of 3 million parameters which we have to compute through, and that is a very very big problem. So for that we compress these images. So here now you can now here what we do operation is called convolution. So the convolution operation is shown by this symbol, that is a asterisk here. So what we do is imagine that this filter right here, is going to be put upon all of these particular chunks. So let's say we overlap this filter that is present right now here, like 1 1 0 0 minus 1 minus 1. So that is being overlapped here. So what will it result into? It will result into 3 into 1 plus 1 into 1 plus 2 into 1, and like this. Also we will do a summation of the multiplications of the two filter and the original kernel. So by multiplying this and summing this, we will get a single number, a single image tensor, and that is being pulled into this particular block at the right. So all you can imagine in this manner that all the numbers, all the tensors which are there in the filter are basically reduced to a particular single image, a single block in the resulting filter. So that is how we convolve an image. So that is the process of convolution. So let's say the next step will be we will move it forward. So earlier we have done till here. Now we have moved one step ahead, and now we have pushed it one more. Now again we are doing the computation again, that what is this multiplied by this kernel, this will result into -4. Then again we do it with here we would have done, so I'm talking about this one. So when we do it here, it will be 0 0 all the place. These will be all 0, these will be all 1, these will be all -1, and 8 plus 2 plus 1 is 11, 7 plus 3 plus 1 is also 11. So plus 11 minus 11 is equal to 0. So that's why this particular term is 0. Then again it move forward to 1, but one more, this will be converted into 8. So this is how we from a initial kernel we convolve it with the filter, and this is how we get a resulting matrix, a resulting tensor in which we have all these images. So you can see how this 6 by 6 matrix is being convolved into a 4 into 4 matrix. So this is the process of convolution. Now what here with the vertical edge detection is that you can see here this particular 0 0 0 line, and this particular this is a pattern of a filter. So this particular filter help us identify all the vertical edges. How's that? I will help you visualize that. So imagine this is one more example which we are taking, in which all of these are 10 along with all these zeros. So what are we going to do in this is that we are convolving it with one more filter, that is the same filter of the vertical edge detection I've mentioned. So all if you can go through really basic, so you can imagine that all these 0 represent a gray format, and all these 10 represent white. So you can see it is a kind of giving us an edge of the like this. And when we convert, and you can see that here you can imagine that this is all these ones are white space, all these zeros are displaying a gray, and all these -1 are displaying black. So when we convolve them, this will give us right ahead this particular edge. It will help us identify that there is a particular edge. So example, you are seeing any image, let's say there is a image of a lightning pole, so like a street light. So of that we have taken an image, and we are trying the neural network to understand. So we need that to understand the vertical edge that is there, that there is a pole. So that this filter will help us identify that there is a vertical edge present here. So when we convolve these and we done the matrix multiplication as I showed you before, to do the whole convolution operation, we will get this matrix that is clearly showing that there is like zeros can be taken as gray and these can be done as white. So this is showing us that there is a vertical edge here. Similarly, you can see these examples. So if we have inverse this, maybe this is 0 one side and gray this side and white this side. Again we will convolve with the same filter. Again we will get a filter, and now this time this filter here is a black filter that is showing that still there is an vertical edge here. So this filter which we have been talking about is a particular crafted filter which has come from research, and this particular filter has helped us to identify what are the vertical edges in this. Similarly, there is a filter for horizontal edge detection as well. So using this, like all top of the row 1, then 0, then -1, this helps us to identify all the horizontal edges which are there. So yeah, here you can see that if we in the a very similar kernel, if we apply this horizontal filter, then this will help us identify the horizontal edges. So now we move forward to our next topic, that is padding. So I hope you have heard about this topic. So padding is basically a technique in neural network to basically preserve the length and breadth, it preserves the dimension. So what we do is right now, whenever we convolve, let's say like in the earlier example as we have taken, we convolve a 6 into 6 kernel with a 3 into 3 filter, that will result into a 4 into 4 resulting, or the final result matrix. But what if I say that there are certain problems in that? This pose some problems to us, that each step output is shrink. So like whenever we have done a step of convolution, the output is shrink from 6 into 6 to 4 into 4, and that in turns let us to throw away a lot of info from edges. So edge because we are taking these particular, and this is being condensed to this particular filter, now we are losing the information from the edges. And as edges are useless, middle part are overlapped more. So let's say we are firstly moving forward with this particular kernel, then we move to this, then we move to this, then we move to this. Again, these edges, or when we move to next, these edges is the least considered. As you can imagine that first we taken this, then we take this, then we take this. So this has also only come one, then we move next, then we come to below the second row. Here also we have taken this, but the edges have been taken a less. So we are essentially throwing a lot of info away. We are not processing the information from these edges, which can be important. To solve this, we have come up with this concept of padding. So that is to solve this exact issue, that before applying the convolution operation that we have shown here, we will pad the image. So what I mean by padding is that we will add an extra layer of matrix, or extra layer of cells, which will be with zeros. So there will be 0 minus infinity, and these will be filled with them. So whenever we take a convolution now, so they are being taken from here. So the 000 will result into zeros, and we are essentially taking this part. So these four blocks are considered if we are taking up block of 3 into 3. So we are taking this. So then these four are the original blocks which will be considered, and the rest are the padding blocks. So what they help is when we move forward. Now I have moved forward from it, then I've taken again these two, then I move forward, then I have again taken these two. Subsequently, when I move down, so then I have to consider this one, and that result into like we are not missing out on the edges, and we are also preserving our dimension of the image. What I mean by dimension is that we are essentially getting 6 into 6 into 4 into 4, but now by applying a padding of 1, by padding of 1 I mean that we are applying like by one more pixel we are adding by all zeros. So by applying a padding of 1, we are getting a 6 into 6 model. So there is a formula for this also. So whenever you have to identify, whenever you want to use into calculations that what is the padding which we are using and what will the resulting dimension, so you can use of this formula, that is n plus 2p minus f plus 1. So n here is 6, then we are multiplying it 2 into padding. What padding we have considered here? We have considered padding of 1. So 2 into 1 minus filter. What is the size of filter? 3. 3 plus 1. So if you solve this, this will come into again as 6. So this is the operation which we took to identify that original size is preserved here. and this is the formula you can apply regardless that you are using the padding or not. So let's say if we are not using padding, and we have done the original was 6 minus 2p. 2p is nothing, it's 0 because we not applied any padding, and the filter is 3 plus 1, then it is also resulting into 4. So that is the original filter which we were getting before applying the padding. So you can remember this. This is this can be a helpful formula, a helpful trick to identify whenever you need to know that what padding are we applying or what will be the resulting dimension. So essentially by padding we are able to identify that we are able to preserve the information. Along with that, we are also be able to, in the final picture, we are also able to preserve the dimension if we want to. So now we move on to next topic, that is there is a very confusion in the convolution. Like whenever you will apply into PyTorch or TensorFlow, or whenever in the commercial grade application, whenever you are sitting down to write the code, so you will many time here there are different examples of talking about valid and same convolution. So you can understand that basically there are two terms used, that is valid and same convolution. Whenever we say valid convolution doesn't account for padding. So you can make a very simple relation in your head that valid means no padding. So whenever we like in the previous slide I show you the formula. So if there is 6x6 image with 3x3 filter, that will turn into a 4x4 resulting image. So that is the part of no padding. So here we are applying no padding at all, and that is generalized as called as valid convolution. If we move forward, we the second part is the same convolution, and that same convolution is used when we pad the output size. That we pad the input so that there is same as the input size. So what I mean is that like we have seen in the previous slide, that this 6x6 has been padded with p is equal to 1, that is padding of 1, so that the output size is same. So the input was 6x6, the output was also 6x6, as in we saw in the previous slide. So these kind of situations where we want that input size to be same of the output size, that we have call as the same convolution. Very simple relation, you can understand that the same means that the dimensions are basically preserved, and valid means the dimensions are not preserved. We are doing the convolution operation as it is. And there is a formula to identify what padding we should do to a particular input image to get the output padding. So as you can see here, let's say if we take the original formula n plus 2p minus f plus 1, and we put that we want the resulting. So this formula is to identify the resulting output dimension, right? So if we equate it to then it get cancelled, and if we put p, so p is equal to f minus 1 by 2. So by using this particular formula, you can anytime identify like what padding you should add to your original input image, so that it will be a same convolution. By same convolution, again I mean so that the input size and the output size will be same. So this is the little trick which we do, so that we identify, and it will be helpful for you to know. So like if the filter size is currently 3, as we have taken in most of our examples, so 3 minus 1 upon 2 is equal to be 1. So that is the same padding which we added in the last example. So we got that 6. If we added a padding of 1, that will result in an output of 6 only. So that is a very useful trick to remember, and I hope that you have understand all of this, and I hope you to catch into the next lecture.